Welcome to Basic Electrical Engineering lecture series. This is a series of lecture videos for the first year engineering and electrical diploma students. In these videos, fundamentals of DC and AC circuits, network theorems, fundamentals of transformers, DC and AC machines, and renewable energy sources are the topics covered. Sufficient number of numericals are worked out in each session to make the concepts clear to the viewers. For a basic idea about the topics mentioned, please watch these videos from the very beginning itself. If you find the videos useful, please subscribe for the channel, like the video, and press the bell icon for notification. Please try to wear a headphone and watch the video for better sound clarity. Thank you all. And now let's start with today's session. So this is the third session. In this session, superposition theorem, reciprocity theorem, Thevnin's theorem, and Norton's theorem. These are the topics covered. Now, superposition theorem. So this is the statement of the theorem. In a linear bilateral network having more than one independent source, the response in any element is the sum of the responses obtained by considering each source separately with all other sources replaced by their internal resistances. So let's consider this circuit. Now, in this circuit, there are two independent sources. And before that, it is a linear circuit. That means current variation is proportional to voltage variation. And bilateral, the performance of the circuit is same in the forward as well as in the backward directions. So this circuit has got two independent sources, one 100-volt source and one 10-ampere source. So in such a circuit, the response in any element, say for example, consider resistor R1. The response in R1 can be found by considering one source at a time. Say, let's consider 100-volt source at a time, at an instance. Then find the response in element R1, whatever it is, say some current we are getting. Then after replacing, so first consider the 100-volt source, replace the 10-ampere current source with its internal resistance. It's a current source internal resistance, let's take it as infinity. That is an open circuit. That is, replace the current source with an open circuit. That means remove the current source from the circuit itself. That means consider only the 100-volt source and find the current through the element R1. Say we are getting some value of current through resistance R1, say from node 1 to node 2. Next, consider the current source and replace the voltage source with its internal resistance. That means the voltage source internal resistance is 0. That means replace the 100-volt source with a short circuit. Consider only the current source and find the response in element R1. We are getting some value of current through R1. If we add these two currents with the proper polarity, then we will get the response, the combined response of both the sources in R1. That is the statement of the theorem. Read the theorem once more. In a linear bilateral network having more than one independent source, here there are two independent sources, a 100-volt voltage source, a 10-ampere current source. The response in any element. Now in this case we have considered the response in R1. You can take any element, R1, R2, R3, R4. like that. So the response in any element can be found by considering each source separately. That means first we consider the 100-volt voltage source, replace the current source with an open circuit, found the current through R1. Next we consider the current source, replace the voltage source with its internal resistance, that is a short circuit, and found the current through R1. Add these two currents with proper signs and we will get the combined effect. That means when both the sources are present, whatever is the current passing through element R1 can be found by adding these two values of current, which we got by considering the sources separately. That is the statement of superposition theorem. Now let's work out this example. Say 100-volt source. There is a resistor in series with it, 47 ohm. The left side there is resistor R3 27 ohm, R1 4 ohm, and R4 23 ohm. So first we will consider only the 100-volt source. Replace the current source with its internal resistance. So current source internal impedance is infinity, we can assume. So replace the current source with infinite resistance, that is an open circuit. That means remove the current source itself from the circuit. And the circuit will look like this. So we are considering only the 100-volt source now. The current source is replaced with its internal resistance, that is infinite ohms or open circuit. Now we have to find the current through R1. So current through R1 can be found by, first we will consider the net resistance of the circuit or net resistance coming across the 100-volt source. So in series with the 100-volt source, resistor R2 is connected, that is 47 ohm. On the left side, there is a 27 ohm resistor. On the right side, this branch is open. So R1 is 4 ohm, R4 is 23 ohm. So total resistance coming on the right side, that is 27 ohms. That means the circuit is like, will become like this, a 100-volt source. Then here a resistor 47 ohms. Here 27 ohm resistor. On the right side R1 plus R4, that is the total resistance. That is 23 plus 4. That is 27 ohms. Sorry. It is 27 ohms. So now these two 27 are coming in parallel and the equivalent of that is 27 by 2. That will be added to 47. So the net resistance of the circuit is 100 volt, 47. This 27 I can bring it to the right side. Equivalent is 27 by 2. So 47 plus 27 by 2, 60.5 is the total resistance coming across the 100-volt source. So the total current supplied by the 100-volt source is 100 divided by 60.5, that is 1.65289 ampere. So this current is 1.65289 ampere. So we have to find the current through the 4 ohm resistor. 4 ohm resistor is coming here. We added that and wrote the total 27. I can split it also. This is 24 and one more resistor is to be connected here. That is 4 ohm. So this is 23, this is 4. So this current is 1.65289. So current through the forearm resistor is 1.65289. Here in the left side, the total resistance is 27. Right side, it is 23 plus 4. That also 27. So this current will equally divide between this 27 and the right side 27. So current is 1.65289 divided by 2. It is 0.826446. So this current is 0.826446 ampere. That is from node 1 to node 2. Let us take this as node 1. This is node 2. So this is node 1. So node 1 to 2. Now in this case, with the voltage source alone, the current is 8.82466 ampere from node 1 to node 2. That is the current through R1 with only the voltage source connected in the circuit. So I'll tell you once more. First we have to simplify this circuit. So 100 volt source in series with its 47 ohm resistor. We are replacing the current source with an open circuit. And the right side total resistance is 23 plus 4, that is 27. Left side also 27. So 27 by 2 is the equivalent of R3 and the combination of R1 and R4. Add this to 47, you will get the total resistance, that is 60.5. 47 plus 27 by 2. This 27 and this 27. Divided by 2 means they are connected in parallel. So equivalent is half of that. So current supplied by the 100 volt source is 100 divided by the net resistance, that is 60.5, 1.65289 ampere. So current through R1 is this divided by 2 or opposite side resistance by sum of the resistance. That equation also you can use. You have to find the current through this branch. That is equal to incoming current coming to the node 1 into opposite side resistance is 27 divided by 27 plus 27, that is 54. So with the voltage source acting alone, the current is 0.82644 ampere from node 1 to node 2. Now consider only the current source, replace the voltage source with its equivalent, that is a short circuit. These terminals are shorted. Now how the current will divide? A 10 ampere is current of 10 ampere is coming to node 2. How it will divide among the resistances? So we have to find the response in this element R1. So what is the equivalent of the resistors on the left side? Equivalent of R3, R2 and R1. On the left side, say take this as the reference point. On the left side, there are three resistors, R2 and R3 in parallel. Equivalent is R2, R3 divided by R2 plus R3. That is 47 into 27 divided by 47 plus 27. That is the equivalent of R2 and R3. That comes in series with R1. That is, we have to add 4 to that. This is the resistance on the left side. Right side, it is 23. So this value 47 into 27 divided by 47 plus 27. Okay. This is the resistance on the left side. Right side, it is 23. So equivalent resistance of R1, R2 and R3. R1, R2, R3. That is 4 plus 27 into 47 divided by, that is 21.1486. This is 21.1486 ohms. Right side, the resistance value is 23. Now the current coming to, so it is the circuit will be, this is the 10 ampere source. The right side resistance is 23 ohm. Left side is 21.1486. 21.1486. This is node 2. Now how the current of a current of 10 ampere will divide between these two resistances? We have to find out the current through R1. That means this current. So that's equal to 10 ampere into opposite side resistance, that is 23, divided by sum of the resistances, that is 23 plus 21.1486. So that is 5.2096 is equal to 5.2096 ampere. That is, this current is 5.2096 ampere. That is from node 2 to node 1. So now if we add these two values of currents, then we will get the net current. That is from node 2 to node 1, if that will be the net, that is 5 on the opposite side, the current flowing through the opposite side is 1.8 to 0.82601 ampere. 1 second. 0.82644. So the net current is 5.2096 minus 0.82644. That means 4.38 ampere from node 2 to node 1. So this current also you have to add. That is 5.2096 from node 2 to node 1, 0.8 something in from node 1 to node 2. So the net is 5.20 minus 0.8 something. That is 4.3832 ampere. This is the net current from node 2 to node, net current. It is from node 2 to node 1. Now we will verify it by considering both the sources at the same time. This node 1, this node 2. Let's use node voltage method. So take the sum of outgoing currents is equal to 0 at node 1. V1 divided by 27, that is this current. Then V1 minus 100 divided by 47, that is the current flowing through the battery branch. Then current flowing from node 1 to node 2, V1 minus V2 divided by 4 is equal to 0. So sum of the outgoing currents is equal to 0. That is V1 divided by 27 plus V1 minus 100 divided by 47 plus V1 minus V2 divided by 4 is equal to 0. Again consider the sum of outgoing currents is equal to 0 at node 2. The current flowing to node 1 is V2 minus V1 divided by 4. Then the outgoing current, a current of 10 ampere is coming to node 2. So current of 10 ampere is coming to node 2. So the outgoing current is minus 10. Then the current flowing through the 23 ohm resistance, V2 divided by 23, outgoing current. So equal to 0. So solve these equations. So we'll get 4.3832. We will get the voltages V1 and V2. So current voltage at V2 is 129, voltage V2 is 129, V1 is 111.65. So the current should flow from node 2 to node 1. It's at a higher potential. V2 is 129.185. 129.185. V1 is 111.65. So the current should flow from node 2 to node 1. That is 129.185 minus 111.65 divided by 4. That is the net current. So it's equal to 4.3832 ampere from node 2 to node 1. This is the proof of superposition theorem. So first case we consider only the voltage source. Replace the current source with its internal impedance, that's an open circuit, and solve for the current between node 1 and 2 or current through the element R1. Then we consider the current source alone, replace the voltage source with its with its internal impedance, that is a short circuit. Again solve for the current from node 2 to node 1. Then now find the sum of that. So when voltage source is considered, voltage source alone is considered, the current is from node 1 to node 2. When current source alone is considered, it is from node 2 to 1. So add these currents with the proper signs. So we get a net current as 4.3832. So consider both the sources at the same time and solve for the current. We are getting the same value of current. That is 4.3832 from node 2 to node 1. Next is reciprocity theorem. The statement is like this, saying in a linear bilateral single source network, the ratio of excitation to response is a constant when the positions of excitation and response are interchanged. So in a linear bilateral single source network, there is only one source in the network. In such a network, the ratio of excitation to response is a constant. So here we are considering the excitation in branch AB. It's a 70.5 volt voltage source. And we are considering the response in branch CD. That is, connect an ammeter here. What is the current through, or what is the response due to the excitation in branch CD? So we can find out either by simplifying this network and find dividing the current among different resistances. We can find out the current, or we can find out the response in branch CD, or we can write node voltage equations and find out either way. So here node voltage equations are written. So we have to find find the current or response in resistor R5, or the response in this 6 ohm resistance R5. So if we go by solve this problem by node voltage method, this is the reference point. Then the equations are sum of the outgoing currents is equal to 0 at node 1. So current through the battery branch is V1 minus 70.5 divided by 12 plus 8. V1 minus 70.5 divided by 12 plus 8, that is 20. Current through the 7 ohm resistor, V1 divided by 7. Then current from node 1 to 2, that is V1 minus V2 divided by 4. Then node 2 equations. sum of the outgoing currents is equal to 0. That is, current flowing node 1 is V2 minus V1 divided by 4. Then current flowing through R4 is V2 divided by 6. Current through R5 is V2 divided by, again V2 divided by 6. So this current both are same. So we can solve this. We will get the V1 is equal to 10.5 volt, and V2 is equal to 4.5 volt. So we have to find the current through response in resistor R5. That is, response in resistor R5 is V2 divided by 6. 4.5 divided by 6 is 0.75 ampere. So response in branch CD is, this is a reference point, 0 volts, 4.5 minus 0. The voltage across 2 and reference, node 2 and reference is 4.5 divided by resistance of the branch is 6. 4.5 by 6 is 0.75 ampere. Now, the positions of excitation and response we have to interchange. That is, excitation is brought to branch CD, 70.5 volt voltage source is brought to branch CD, and response, we have to find the response through this branch. I'll connect an ammeter here. Now again we have to find the current in branch AB. So it is due to this we interchange the position of excitation and response. Excitation is brought to branch CD. The response indicator and ammeter is connected in branch AB. Now we have to find out the current through branch AB. So we can simplify this network and divide the currents and find the response in branch AB. Or in this case, it is done by mesh current method. I1, I2, I3. So writing mesh current equations. So here R1 is 8, R6 is 12, so 20 minus I1 into 20, then minus I1 minus I2 into 7. So mesh current equation, this is the clockwise is the direction of the loop or the mesh. So the resistance R6 is 12, this is 8. So minus I1 into 12 plus 8, minus I1 into 20, then minus I1 minus I2 into 7 is equal to 0. For the second mesh, minus 7 into I2 minus I1, minus 4 I2, and for this minus I2 minus I3 into 6. And for the third loop, minus I3 minus I2 into 6, then minus 6 into I3 for this. And this is a fallen potential, minus 70.5 is equal to 0. In the direction of the loop, it is a fallen potential. So because the loop is directed from positive of the battery to the negative. So solve this, find I1, that will be the response in branch AB. So simplify it. So I1, I2, I3 is equal to inverse of this matrix. Let's take it as a A inverse into 0, 0, 70.5. You will get I1 is minus 0.75, I2 minus 2.89, I3 is minus 7.32. So all the assumed directions of current, to reverse it, opposite is the direction of the current, actual direction of the current. Now we are getting response in branch AB is 0.75 ampere. So we have interchanged the positions of excitation and response. We are getting the same value for the same excitation. We are getting the same response. Same excitation means the ratio of excitation to response is 1 in this case. Because in the first case, the excitation was 70.5 volt in branch AB. The response we found in branch CD. In the second case, uh, the excitation is same value of excitation is put here, and we found the response in branch AB. So excitation to response ratio is 1 in this case. But if we change the ratio, that is, in the second case here in the what example we worked out, the excitation value was 70.5 in branch CD. So instead of that, if we reduce it to a lower value, so instead of 70.5, we are applying a percentage of that, 40%. You can apply even above 70.5 also. So if the excitation is reduced to 40% of its original value, this will be 28.2 volts, 40% of 70.5. Again find the excitation again find the response in AB, response indicator we are putting here. So we'll get minus 0.3 ampere. Minus 0.3 means again we are using mesh current method. I1, I2, I3. So solve for I1. We'll get minus 0.3 ampere. That means actually current is in the opposite direction. This is minus 0.3 ampere or plus 0.3 ampere in like this. So the excitation is reduced to 40. What was the response in the first case? 0.75 ampere. Now what is the 40% of 0.75? 40% of 0.75 is 0.3. That means excitation to response ratio is different also. That is, the theorem states that the ratio of excitation to response is the same even though the positions of excitation and response are interchanged. Now here in second case, we applied 40% of the excitation and the response we got is 40% of the response which we got it in the first time. So the ratio remains constant. That is reciprocity theorem. Now next is Thevnin's theorem. So the statement of the theorem, that's in a linear active resistive network which contains one or more voltage or current sources can be replaced with a single voltage source and a series resistance. So Norton theorem also a similar statement in a linear active resistive network which contains one or more voltage or current sources can be replaced with a single current source and a parallel resistance. So according to the Thevnin's theorem, A linear active resistive network containing one or more voltage or current sources can be replaced with a single voltage source and a series resistance. Now in this network, say two terminals are provided, A and B. That means we have to replace the network on the left side with a single voltage source in series with a single resistance. The network to the left of A and B is to be replaced with a single voltage source in series with a single resistance. So if we solve the problem, to find the voltage source, so this circuit on the left side is to be replaced with a single voltage source and a series resistance. That means the equivalent circuit should look like this. So here whatever is there on the left side of A and B should be replaced with a single voltage source and a series resistance. And the magnitude of this voltage source, say let us call it as V Thevnin, it is the open circuit voltage between terminals A and B. That means if we measure the voltage across A and B with a voltmeter, whatever voltage you are getting, that is the magnitude of this VTH, V Thevenins. Then the magnitude of the series resistance is replace all the sources with their internal resistances and measure the resistance across terminals A and B. Replace the sources, all the sources with their internal resistance. So in this case, the voltage source is to be replaced with a short circuit and current source should be replaced with an open circuit. And measure the resistance across terminals A and B. That is the value of RTH. So the left side, that means the circuit coming on the left side of terminals A and B in this case, we can replace it with a single voltage source and a series resistance. That means a complex network can be reduced to a very simple network. Now to find the open circuit voltage between A and B, we'll solve the problem by node voltage method. So this node is marked as X. So again, by node voltage method, take the sum of outgoing currents is equal to 0. So current flowing through R1 is Vx minus 10 divided by 5. Then in this current, in this branch, the current is 1 ampere. It is flowing towards node X, so outgoing current is minus 1. Then from node X to node A, this is node A only. Node X to node A, Vx minus Va divided by 15. Likewise, we can take the sum of outgoing currents at node A also equal to 0. So current through R3 is Va minus Vx divided by 15. Then current through R4 is Va minus 0 divided by 10. Solve for Va. So Vx 12.5 and Va 5 volts. So we need Va. This is 5 volt with respect to reference. This is the reference point. That means VAB is equal to 5 volts or V Thevenin is equal to 5 volts. Now we have to find the equivalent resistance between terminals A and B. So for that, replace the voltage source with a short circuit and current source with an open circuit. I'll draw the network here. This is R1 5 ohm. The voltage source is replaced with a short circuit. This branch is open. Current source is to be replaced with an open circuit. So this branch is open. Here it is 15 ohm. Then between A and reference it is 10 ohm. So this is the network. This is 10 ohm. This is 20 ohm. So voltage source is replaced with a short circuit and current source with an open circuit. That means this branch we have to avoid. So R1 will be there in the circuit, that is 5 ohm. R2 will not be there. The branch itself is taken out. So from Vx to Va, or X to A, the resistance is 50 ohm, 15 ohm. Then between A and reference, it is 10 ohm. So 20 in parallel with 10. 20 into 10, that is 200 divided by 30. That is the equivalent resistance. That is 6.666 ohm. That is 20 in parallel with 10. 20 into 10 divided by 20 plus 10 is equal to 200 divided by 30 is equal to 6.6667. So our Thevnin equivalent resistance is 6.666. So the network to the left of this points A and B, we have replaced with a single voltage source with a series resistance. And the magnitude of the voltage source is the open circuit voltage between A and B. So the open circuit means without any elements, resistor elements connected between A and B. That is the open circuit voltage. So that we found out by node voltage method. So VA is the potential difference between A and B, because this is a reference point. So by node voltage method, VA is equal to 5 volts we got. And to find the equivalent resistance, all the sources are replaced with their internal resistances. Voltage source is replaced with a short circuit and current source with an open circuit. So when voltage source is replaced with a short circuit and current source with an open circuit, the resistance is reduced to this form. So this is 5 and 15. It is total 20 ohm resistance here. The shunt branch, there is a 10 ohm resistor. So now 20 and 10 are connected in parallel. Equivalent is 6.667. So the network is across terminals A and B is replaced with an equivalent voltage and a series resistance. The voltage is the open circuit voltage between A and B, in this case 5 volt, and the equivalent resistance is 6.66 ohm. So this is the circuit. Now this is the Thevnin equivalent circuit. Now to find the Norton equivalent, just short these points and find what is the current from A to B. That is 5 divided by 6.66, that is 0.75 ampere. If you short it, you will get 0.75 ampere. That is the Norton equivalent current, 0.75. And the equivalent resistance is same resistor, 6.6 connected in parallel. So these two circuits are equivalent. That is 5 volt in series with 6.66 and 0.75 ampere in parallel with 6.66. Both are equivalent networks. Because if we connect a load resistance across A and B, whatever is the current flowing in the first case, same current will get in the second case also. So So connect a load resistance of 3.33 across both the resistors. So here this is the Thevnin equivalent, 5 volt in series with the 6.66 ohm. The load resistance is 3.33 ohm. And what is the load current? Load current IL is equal to 5 divided by 6.666 plus 3.333, that is 10, or 5 by 10 is zero point 0.5 amp. Now in the second case also connect a load resistance of 3.33 ohm across terminals A and B. Here the Norton equivalent current is 0.75 ampere. This is 6.66. This is 3.33. So IL can be found by current division formula, that is 0.75 into opposite side, that is we have to find the current through R2. So opposite side resistance is R1, that is 6.666 divided by 6.66 plus 3.33, that is 10. So that is again 0.5 ampere. So these two circuits are equivalent. So according to Thevenin's theorem, the equivalent circuit, there is a voltage source and there is series resistance. And according to Norton's theorem, there is a current source with a parallel resistance. So we found out both the Thevenin equivalent as well as Norton equivalent. Now if you are finding out across another pair of terminals, so in this case the terminals are A and B. So what is the Thevenin equivalent across terminals A and B? In this case, this circuit is to be replaced with a single voltage source and a series resistance. So first we have to find out the OC voltage between A and B. Again, that we can find using node voltage method. That is node voltage in write the node equations, the outgoing currents. VA minus 10 by 5 plus VA minus 10 by 5. This is minus 1 ampere, sorry, minus 1. Outgoing current is 1 ampere, incoming current is incoming current is 1 ampere. Current to node A is 1 ampere. So outgoing is minus 1. Then VA minus VB by 50. This is capital A. VA minus VB divided by 15 is equal to 0. Then for node B, VB minus VA divided by this resistance is 15 plus VB divided by 10 is equal to 0. So solving VA 12.5 and VB 5. VA, this is 12.5 volts, this is 5 volts. That is VAB is equal to 12.5 minus 5. It's equal to 7.5 volts. So V Thevenin is equal to 7.5 volts. Now to find the equivalent impedance, equivalent resistance between terminals A and B, this is terminal A, terminal B. Already there is a 15 ohm resistor here. Then replace the voltage source with a short circuit and current source with an open circuit. A2 reference is 5. And then B2 reference is 10. This branch is out. This is the circuit. So between A and B, this V1 is replaced with a short circuit. So A2 reference, in that branch there is a 5 ohm resistor. Then this current source is replaced with an open circuit. This branch is taken out. Then B to reference, it is 10 ohm. B to reference, it is 10 ohm. So between A and B, 15. This branch also has got 15. So between A and B, there is one 15 here, one more 15. So between A and B, the equivalent resistance is 15 divided by 2 is equal to 7.5 ohm. So 7 volt in series with the 7.5 volt in series with the 7.5. That is the equivalent resistance. That is the equivalent circuit. 7.5 volt in series with a 7.5. So to find the Norton equivalent, short the terminals A and B and find the current. That is 1 ampere only. So 1 ampere in parallel with the 7.5 is the Norton equivalent. 1 ampere in parallel with the 7.5. So if you connect a load resistance across these two, the current through the load resistance will be the same. Or if you connect a load, say for example, a 7.5, this is simulation result only. A load resistance of 7.5 is connected across A and B, and the current is 0.5 ampere. So in this case, if we connect a load resistance of 7.5, what is the load current? IL is equal to 7.5 divided by 7.5 plus 7.5, 15. That is 0.5. In this case, if we connect a load resistance of 7.5 ohm, incoming current is 1 ampere. It is dividing between these two 7.5, so it will equally divide. So load resistance is equal to 1 into 7.5 divided by 15, that is 0.5. In either case, you will get a 0.5. So in the original network itself, if we connect a load resistance of 7.5 across terminals A and B and solve for the circuit, you will get 500 milliampere, that is 0.5 ampere through the load resistance. So that is Thevnin's and Norton's theorem. So that's all for today. Thank you very much for attending this session. So if you like the video, please subscribe for the channel and share the video among your friends. Thank you. Welcome to Basic Electrical Engineering lecture series. This is a series of lecture videos for the first year engineering and electrical diploma students. In these videos, fundamentals of DC and AC circuits, network theorems, fundamentals of transformers, DC and AC machines, and renewable energy sources are the topics covered. Sufficient number of numericals are worked out in each session to make the concepts clear to the viewers. For a basic idea about the topics mentioned, please watch these videos from the very beginning itself. If you find the videos useful, please subscribe for the channel, like the video, and press the bell icon for notification. Please try to wear a headphone and watch the video for better sound clarity. Thank you all. And now let's start with today's session.